Hey guys, so we're going to try a lesson here. It's a little bit tricky because there's lots of demos in this lesson, so I'm going to try to do the best without a cameraman, but we'll start off with the sample diploma questions here. So give them a go, pause the video, and then see if you can do it. So if the charge on a point source is that, and the electric field strength is that, then the electric field strength at a distance of that is. So this would be E equals KQ all over R squared. And no need to rearrange anything at all. Right, so our K is at 8.99 times 10 to the 9. Our charge in the question says it's 0.5, and it's just coulombs. And then on the bottom, we have our radius, which is 0.25 meters. And a lot of people get this wrong because they forget to square that. Don't forget to square it. And you get 7.19 times 10 to the negative 10. So D is the correct answer. Given the information above, the magnitude of the gravitational field strength experienced by the object on the surface of Mars is. Right. So this is a G equals GM all over R squared question. And you can find that G value in your data booklet. That's when we saved 6.67 times 10 to the negative 11. And we multiply that. So we want to find about Mars. So we want to use the mass of Mars, 6.42 times 10 to the 23. So that's our mass. And then we divide it by our radius. And we can see that the radius of Mars is 3.4 times 10 to the 6. And we want to square that because it's a radius. And we get 3.70, so that would be our answer, 3.70. Okay, and which of the following planets would have the greatest gravitational field strength? So we're looking at this formula. And what a lot of people will select B as the answer, but B is not the correct answer, right? If we double the mass, then we're going to double the G, right? But the thing that's going to make the biggest impact on it, just erase our, oops, there we go. The thing that's going to make the biggest impact is if we half this. Remember that we half it squared because R is squared, so we half that squared. So instead of being, we don't do anything to the top. 1 squared is 1. 2 squared is 2, so this is the 1/2, and then the 1 is just on the top. So it ends up being 1 over 4, which is the same thing as 4. So if we half the radius, we 4 times the gravitational field strength, right? So because the radius is squared, it makes a bigger impact. So C is actually the correct answer. Okay, it's that inverse squared relationship that we talked about. In 31, trying to find electric field strength. And they want to know the field strength at 3R, so 3 times away from that. So 3 times this radius. Okay, so we can just calculate that if we want to. We can use E equals KQ all over R squared. So our K is 8.99 times 10 to the 9. And then our charge is 3.9 times 10 to the negative 11. Right, and then our radius, so we want to triple our radius. So our radius before was 0.25. And then we can square this. So we want to square the triple because we want to triple that, and we want to square it so outside of our brackets. And we end up getting 2.49, which is A. So the other way that you could do this is if we triple our radius. So they gave us the E before is 22.4. But if we go 3 times as far away, it's going to be, because that R is squared, it's going to be 1/9 as big. It's going to be 9 times smaller. So if you went 22.4 in your calculator, and you divided it by 9, because it's going to be 9 times smaller, you can see you basically get the exact same answer. There's a little bit of rounding in there, that's why you don't get exact same, but 2 ways of doing it. So, yeah. Okay, so motors and generators is going to be a tricky lesson. Just, just have some patience with me with the camera work, because it's a little bit tricky doing this all by yourself. So, curriculum, you need to describe the effect of a conductor moving through a magnetic field and inducing an electrical current. Distinguish between alternating current and direct current in terms of electron flow and electric field. Describe the advantage of AC over DC for transmitting and using electrical energy, and compare the general design and function of a DC motor and generator. Okay, so when electricity flows through a wire, it creates a magnetic field that wraps around the wire. So electricity can actually create a magnetic field, right? So if I send current through this wire, what happens is there's a magnetic field that wraps around it. And what can we use to detect it on a magnetic field? Well, we can use a compass. Right? So if I stick a compass in here, it'll point that way. And then if I stick a compass in here, it'll point that way. The compass will sort of show that this wraps around like that. So if you just have one wire, the magnetic field is really weak. So what we can do to make things stronger is make more loops, because every loop that we make, they have their own magnetic field. So every loop has its own magnetic field. So the more loops we have, the stronger it is. So we can either increase the current running through the wire, that makes it hot, or we can wrap more coils around the wire, and we create something called a solenoid or an electromagnet. So a coil of wires works the exact same as a bar magnet, except you can turn it on and off. So it's called a solenoid or an electromagnet. And what happens when 2 magnetic fields interact? So if you have a north and a south, and a north and a south. So if you have these 2 magnetic fields, well, these guys are going to repel each other. So I'm going to show you a solenoid here. So this is just, so I have it hooked up to an electricity source, and then I have rafts of wires around here, and I just set up some compasses so we can see the magnetic field around it. So I'm just going to turn the electricity on. So there's the electricity on, and you can see that the compasses snap to attention. And what the compasses tell us, I had to put them on erasers to make them a little bit bigger. So you can see that the north end of the compass, oops, this guy's all jammed up. So the north end of the compass is pointing this way. And then what the heck? My compasses are broken. I think it's because I have a strong magnet close by. Let me just move this a little bit further away. Oh man. That's why I use simulations. Okay, so the north end is pointing here, which shows it's the south end. And then as I go around, you can see on the side, the north is pointing that way. There we go. And then I get the south end pointing here, but you probably can't even see that because of the camera angle. But the south end is pointing there, and the north end is pointing there. So we have our magnetic field goes around in circles like that, and you have a north end and a south end. So I'm just going to bring it back to our picture here. Yeah, so my compass, if this is my north end, my compass should point away. Right? And this is my south end, my compass should point towards. And that goes in a circle, but my compasses were being wonky because I have a bunch of magnets set up over there. Okay, so what happened in this situation? So we have a current running through this, right? So it creates its own north and south magnetic field, but then I put a permanent magnet close by. Right? Well, what's going to happen is my north is going to try to go to my south, and my south is going to try to go to my north. And what I can get is I can get this ring, I can get it to spin in a circle, right? So I've set that up over here. So let me show you that. Just got to move the camera over here. Yeah, this guy right here. So what I have is I have a magnet, and this magnet has its own magnetic field, and then I have a battery. So I can get current to move through this wire. And I have a whole bunch of coils of wire here. So if I stick this in here, now we have the battery and we have a current flowing through it. So when we have current flowing through it, we get motion. Right? So you can see that it's moving on its own. So what's happening in this situation is inside of this coil, we get a magnetic field. When it's attached to the battery, we get a magnetic field. And we have a north side and a south side. And this battery has a north side and a south side. So the induced current in this coil of wire interacts with the magnetic field from this permanent magnet, and you get motion. And this is how a motor works. Here it goes. Okay, that's how a motor works. That's the simple design of a motor to work. So for a motor to work, you need a coil, right? You need to run a current through it, and you need to put it in a magnetic field. But one of the problems that you get is, well, if we go back to this picture, once my north has reached my south and my south has reached my north, well, all of a sudden, it's going to stop spinning, right? But if we switch the direction of the current, what we do is we switch this to south and this to north. So now you'd have your south by your south and your north by your north, and they would repel each other and they keep spinning. So what we need to do is we need to switch the direction of the current every half turn. And the way that we do that is through a split ring commutator. So a split ring commutator switches the direction of flow every half turn in the motor. So this changes the direction of the magnetic field every half turn, and this is what we use in DC, which stands for direct current motors. Okay, so let me switch screens here. I have this set up here. Let me just show you. So this is called a St. Louis motor, and this is just a very simple motor. So here, let me use a pencil. Here I have split ring commutators. So if I, oops, still have my current on. So if I hook up direct current to that, what's going to happen is the electricity is going to flow from this red wire into here, into this brush, and then this brush is hooked up to this side, which is hooked up to this electromagnet. But when it does 1/2 spin, now this brush is hooked up to this side, which is a different electromagnet. So every half turn, it switches which current it goes into. So 1/2 turn, the current goes into this one, 1/2 current, the current goes into that one, and it switches that direction of the current. So if I turn the current on, you can see it spins. But one of the big disadvantages to this type of motor is you can see that it's not spinning very fast. There's a lot of friction in this setup. And that's the big downside to split ring commutators, as we'll talk about later. So I'm shutting the power off to that. Okay, so you can see it's hooked up to this brush this side, and then it does a half turn, it switches to the other side. Okay, you don't really, like, if that's confusing, there's going to be no questions about how split ring commutators work. You just have brushes and then a side, and then when this flips 1/2 turn, it makes the current go the opposite way. So what you need to know about motors is that a current flowing through a wire causes a magnetic field. So you hook this wire up to a battery, and you cause a north and you cause a south. So current moving through a wire causes a magnetic field. If you stick a permanent magnetic field in between there, it causes the magnetic field that's induced in the wire and the permanent magnetic field to interact, which causes a force, which causes a movement, and you get a motor. Okay, that's what you need to know. So, yeah. You also need to know that for DC, you need a split ring commutator. So anytime you see a split ring commutator, it means it is DC, direct current. Okay, generators work a little bit differently. So a generator, the computer just froze up. Uh-oh, I hope this doesn't wreck my video. I'm still recording. Yeah, looks like I'm still recording good. So a generator is a little bit different. Oops. Yeah, let me open this up yet. No. Sorry, I didn't have this pre-opened beforehand. And open, please. Oh man, this computer's freezing right up. Just froze it again. There it goes. Yeah. Sorry about that. Let's go back to this. Okay. Still recording. So when a wire moves near a magnet, or a magnet moves near a wire, a current can be induced. So I'm going to show you that with this little simulation here. So this is our electromagnet, right? We do a direct current. A battery is a direct current. We run it through a wire. You can see that my north end of my compass is pointing to this end, so this is south. And then it loops around. And then this is north, so this was an electromagnet. But what we can do is we can take this magnet, and if I just put it by the loops, it doesn't do anything. But if I move it by the loops like that, you can see that I make electrons move. So as I pull it away, I make electrons move. As I pull it towards, I make electrons move. Right? So if I'm constantly moving this thing, then I always get electrons to be moving. And what you can create is you can create a generator with that. So instead of me just moving it all the time, maybe you have a source of water, right? And the source of water can make this magnet move. So if I have a moving magnet by a coil of wire, then I get a generator and I generate electricity. But you can see the electrons are moving back and forth, back and forth. So this is alternating current. So I'm generating alternating current. But if I have a battery hooked up to it, you can see the electrons slow them down. We're always moving in the same direction. That's direct current. Alternating current is when they're moving back and forth. Okay, so motors turn electricity into motion, which is kinetic energy, and generators turn kinetic energy into electricity. So I have one more little demo for you. I'll move my motor out of the way. So this here, let's zoom out a little bit, some special effects. There we go. So this is my generator. And what I need to do to generate electricity is I need to provide that work myself. I need to make something move. So these guys here are magnets, and inside of here is a coil of wire. So when I move that coil of wire by the magnets, I can generate electricity. And this thing is ancient, so I'm going to shut off the lights, and then when I turn it, you can see the light bulb lights up just a little bit like that, right? And this thing's old, so it doesn't produce a lot of electricity, but it's a good demo. Okay. So with it, so this is a DC motor design, and with that DC motor, you have this split ring commutator. So you have that split in between there, and you're pulling that crank, and you're lighting up the light bulb. An AC generator, sometimes you'll see this term called slip rings, which sounds a lot like split rings, but it's always two of them, and there's slip rings, and you'd have to be able to identify that as this is an AC generator, and just having one here as a split ring is a DC generator. So DC is split ring, AC is slip ring. So some motors run on direct current, where others where the current flows in one direction, and some motors run on alternating current AC, where the current switches back and forth every 60 times. So here's a video that shows what happened with AC and DC. So when they first started making electricity, they didn't know whether to use AC or DC. And Edison, Thomas Edison, you've probably heard of him, he was for DC, and he tried to make all of America on DC. And then there was Tesla, Nikola Tesla, which you've probably heard of as well. He wanted to run it on AC. And yeah, so here's a video. It's long, but it's good. It's about 40 minutes. So watch the video, and yeah, and it there's going to be test questions on this video, so you got to watch it, and you got to know what the advantages and disadvantages of AC and DC. So it's a good video, so watch it and enjoy.